Okay, welcome to the next video in the mathematical logic sequence, talking about propositional logic, and this time talking about satisfaction, entailment, equivalence, and tautology. So this video will be all about semantic concepts, and I'm doing this a little bit out of the order that it appears in the textbook, but I think that this is sort of better preparation for talking about disjunctive normal form in a couple videos. So a very simple word that we'll define but use a lot is satisfaction. And so we say that a model satisfies a formula if the model evaluates that formula to the value 1, right? So basically assigns it true, right? So that's what it means for a model to satisfy a formula. Now we extend this to satisfying an entire set of formula, which really just means that the model satisfies every formula in the set, right? So this is a claim about for all of the elements, right? If there's even just one that it doesn't satisfy, then it doesn't satisfy the set. We have some notation for this. So when W satisfies the set X, we write with this double turnstile symbol. Here's just a quick example, probably really clear what's going on there, so I won't talk it out. And one further piece of vocabulary on this slide, which is that a set is called satisfiable if there is at least one model which satisfies it. So, right, we can see that the previous example shows us a satisfiable set because there is a model which satisfies it. And we could also just give a quick example of an unsatisfiable set by writing this down. So it should be fairly immediately obvious that no model will ever satisfy this set. Next, we define the concept of entailment. So we will say that a formula phi entails another formula psi if every model satisfying phi also satisfies psi. So again, just to give a quick example of that kind of thing, we could say, for instance, that P1 satisfies negation, negation P1, to give an especially trivial example, but that is an example of one formula entailing another formula. Here's another example, P1 conjunction P2 entails P1. Onto the concept of equivalence. So we say that two formulae are equivalent to each other if each one entails the other. An example would be this familiar distribution law, which really is just the equivalence of some two formulae. Finally, we define tautology and contradiction. So a formula is called a tautology if it is equivalent to the canonical tautology. Recall that that top symbol was a piece of syntactic sugar for the sentence P1 disjunction negation P1. And so certainly, right, P1 disjunction negation P1 just is the same thing as that top symbol, right, verum, and it is equivalent to itself, so that technically counts. So that is a tautology. A formula is a contradiction if it is equivalent to falsum by basically the same sort of ideas. And although I am stating it with equivalence, and that is true and so on, but it is kind of interesting that you actually don't need full equivalence, right? If verum implies your sentence, that is enough for the sentence phi to be a tautology. It would immediately follow, if that is true, that phi also entails verum. And you could also do a similar thing with falsum, except you'd have to swap it around, right? So if your sentence entails falsum, then the sentence is a contradiction. Falsum would entail it. In fact, there's a bit of a triviality here because every sentence entails verum, and falsum entails every sentence. Okay, now the book gives a long list of famous equivalences, and I take that material to be familiar enough from a symbolic logic course that I won't necessarily go over it, but, you know, they are generally named the associative law, the commutative law, there's like idempotence, and a bunch of others. So anyway,